Bismillahirrahmanirrahim. Assalamu alaikum. We will start our second lecture. We start with events. Anything that can happen in space-time is called an event. It can be two particles colliding or emission of light from a flash, a particle just passing by, or just anything else that can be imagined. We can characterize each event by its spatial locations and the time at which it occurs. Idealistically, events happen at a single mathematical point. For that, we need to assign some set of four coordinates like t, x, y, z. स्पेस टाइम में जो भी चीज़ अकर करेगी हम उसको नाम देंगे इवेंट का। और इवेंट कोई भी चीज़ हो सकती है। अगर फॉर एग्ज़ाम्पल कोई दो पार्टिकल्स आपस में कोलाइड करें या फ्लैश लाइट अमिट हो, तो हम किसी भी किस्म का कोई वाक़या जो पेश आ रहा होगा स्पेस टाइम में, हम उसे इवेंट का नाम देंगे। और इवेंट को डिस्क्राइब करने के लिए हमें स्पेशियल लोकेशन देनी पड़ेगी और साथ में टाइम को बताना पड़ेगा। तो इसके लिए हम कोऑर्डिनेट्स का सेट यूज़ कर सकते हैं एक्स वाई जी, और साथ में टाइम के कोऑर्डिनेट्स भी ऐड करना पड़ेंगे टाइम टी। आवर नेक्स्ट टॉपिक इज़ द इंटरवल। इंटरवल स्पेस टाइम में दो इवेंट्स अकर कर रहे होंगे तो उनके दरमियान में जो डिस्टेंस होगा उसको हम इंटरवल का नाम देंगे। This space-time interval gives the distance between two events in space and time. It is a generalization of the Pythagorean theorem. The distance between 2 points in Cartesian coordinates is given by expression d is equal to x1 minus x2 to power 2 plus y minus y to power 2 plus z minus z to power square 2 अंडर रूट। ये फार्मूला बिल्कुल ऐसे ही है जैसे हम एक्स स्क्वेयर प्लस वाई स्क्वेयर प्लस जी स्क्वेयर अंडर रूट कैलकुलेट करते थे डिस्टेंस को मेजर करने के लिए। इसी तरह हमने अगर इंटरवल कैलकुलेट करना है तो फिर हम डिस्टेंस का फार्मूला यूज़ करेंगे कार्टेशियन कोऑर्डिनेट्स में और दो पॉइंट्स के दरमियान में डिस्टेंस मेजर करेंगे। While describing interval in special relativity, we generalize the above formula where we consider the distances in space and also time together. Let's consider an event that occurs at E1 whose coordinates are c, t1, x1, y1, z1, and a second event occurs at point E2 whose coordinates are c, t2, x2, y2, z2. Then we can calculate the space-time interval, which we denote by delta s to power square, is given by delta s whole square is equal to c square. C, the speed of light is constant, therefore we write it as common, and c square into, then we have t1 minus t2 square minus x1 minus x2 square minus y1 minus y2 square minus z1 minus z2 whole square. Or we can write it as delta s square is equal to c square delta t square minus delta x square minus delta y square minus delta z square. An interval can be designated time-like, space-like, or null. It depends on the value of delta S square. If delta S square is greater than 0, we can say that interval is time-like. Delta S square is less than 0, then it will be space-like, or delta S square is equal to 0, we can say it as null respectively. If the distance between 2 points or if the distance between two events is infinitesimal, that is x1 is equal to x, x2 is equal to x plus dx, or delta x is equal to x plus dx minus x, then it will be equal to dx. Then the interval is given by ds square is equal to c square dt square minus dx square minus dy square minus dz square. From the definition of interval, we can define the proper time. The proper time is the time measured by an observer's own clock, is defined as deta square is equal to minus ds square, which is equal to minus c square dt square plus dx square plus dy square plus dz square. जब ऑब्जर्वर अपनी क्लॉक से टाइम मेजर करेगा तो उस टाइम को हम कहेंगे प्रॉपर टाइम, और प्रॉपर टाइम को हम रिप्रेजेंट करते हैं डीटा से, और जो प्रॉपर टाइम है उसकी वैल्यू नेगेटिव होगी, नेगेटिव वैल्यू होती है इंटरवल की। डीटा स्क्वायर इज इक्वल टू माइनस डी एस स्क्वायर। Interval is important because it is an invariant quantity. It means interval remains the same in different reference frames or for different observers. It means while observers in motion with respect to each other will assign different values to space and time differences, they all agree on the value of the interval. Our next topic is Lorentz transformations. It is the set of equations in relativity physics that relate the space and time coordinates of two systems moving at a constant velocity relative to each other. These equations were developed by the Dutch physicist Lorentz in 1904. Lorentz transformations express the relativity concept that space and time are not absolute, that length, time and mass depend on the relative motion of the observer. लॉरेंट्स ट्रांसफॉर्मेशन बेसिकली हमें ये बताती हैं कि स्पेस और टाइम एब्सोल्यूट नहीं है, बल्कि लेंथ, टाइम और मास की वैल्यू जो है वो डिपेंड करती है रिलेटिव टू द मोशन ऑफ द ऑब्जर्वर. द स्पीड ऑफ लाइट इन अ वैक्यूम इज़ कांस्टेंट as we already studied and independent of the motion of the observer or the source. We have an observer in frame S prime moving at a speed v along the x-axis. The transformation equations can be written as x prime is equal to gamma into x minus vt, y prime is equal to y, z prime is equal to z, t prime is equal to gamma into t minus vx over c square, where gamma is called the Lorentz factor. It is the factor by which time, length and relativistic mass change for an object while that object is moving. टाइम, लेंथ और मास के अंदर जो चेंज आएगा ऑब्जेक्ट के, उसको हम रिप्रेजेंट करते हैं एक फैक्टर से, जिसको हम रिप्रेजेंट करते हैं, जिसके लिए सिंबल हम यूज़ करते हैं गैमा, और इसे हम कहते हैं लॉरेंट्ज फैक्टर। इसकी वैल्यू होती है गैमा इज इक्वल टू 1/1 माइनस वी स्क्वेयर ओवर सी स्क्वेयर अंडर रूट, और गैमा इज इक्वल टू 1/1 माइनस बीटा स्क्वेयर अंडर रूट, where beta is the ratio of V to C. We can write beta is equal to V over C. Here V is the relative velocity between inertial reference frames, C is the speed of light in a vacuum, and T is coordinate time. For the derivation of Lorentz transformation or these four equations, please refer to the book Relativity Demystified. You can find the derivation of Lorentz transformation from there. From the Lorentz transformations for space-time, one can also derive the Lorentz velocity transformations, which we can write as ux prime is equal to dx prime over dt prime, which is equal to dx minus v dt over dt minus v over c square dx, which we can also write as ux minus v over 1 minus ux v over c square. Similarly, we can write the same equation along the y and z directions, like uy prime will be equal to uy minus v over 1 minus uy v over c square, and similarly uz prime will be equal to uz minus v over 1 minus uz v over c square. We have limiting cases here depending on the velocity. Number 1, when v is very small as compared to speed of light c, then we will have ux prime will be equal to ux minus v over 1 minus ux v over c square, which is approximately equal to ux minus v. Number 2, when ux is equal to c, then ux prime will be equal to c minus v over 1 minus c v over c square, which is equal to c minus v over 1 over c into c minus v. We can cancel c minus v above and below, then we get 1 over c, which can be written as equal to c. So when ux is equal to speed of light, then ux prime will be equal to c. Means for both observers the value or the velocity transformation will be the same. Ux is equal to c and ux prime will also be equal to c. Our next topic is 3 basic physical implications. There are 3 physical consequences of special relativity that emerges from the Lorentz transformations. These are time dilation, length contraction, and a new rule for composition of velocities. We will go through one by one these 3 physical consequences of special relativity. First of all, time dilation. To describe time dilation, let's imagine 2 frames f and f prime, which are in the standard configuration. That means frame f prime moves at uniform velocity v with respect to frame f, an interval of time delta t prime as measured by an observer in frame f prime, which is seen by an observer in frame f, can be written as delta t is equal to 1 over 1 minus beta square under root delta t prime, which is equal to gamma delta t prime. The equation for time dilation is delta t is equal to gamma delta t prime. This expression tells that the clock of an observer whose frame is f prime runs slow relative to the clock of an observer whose frame is f by a factor of 1 minus beta square under root. From this equation we can say that time gets delayed or becomes slow when an object approaches the speed of light. So we can say that time dilates or runs slow. Next we will discuss length contraction. Since time intervals now depends on the reference frame, length will also depend on the reference frame. The length measured by an observer at rest relative to the object is called the proper length. We will use this definition to find the formula for the length contraction. Let's again consider two frames in the standard configuration. At fixed time t, measured distances along the direction of motion are related by delta x prime is equal to 1 over 1 minus beta square under root delta x. That is, distances in f prime frame along the direction of motion appear to be shortened in the direction of motion by a factor of 1 minus beta square under root. From this expression we can say that length of an object appear to be shortened when the speed of an object approaches to the speed of light. Number 3 is the composition of velocities. Now we will imagine three frames of references which are in the standard configuration. Frame f prime moves with velocity v1 with respect to frame f, and frame f double prime moves with velocity v2 with respect to frame f prime. न्यूटोनियन फिजिक्स के मुताबिक फ्रेम f double prime will move with velocity v3 is equal to v1 plus v2 with respect to frame f, which is a simple velocity addition law. This simple velocity addition law will not hold if velocities are fraction of the speed of light. Therefore, to obtain the correct relation, we simply compose two Lorentz transformations and then we will find the velocities in different frames of references. These are the three physical consequences of special relativity which arises from the Lorentz transformation: the time dilation, length contraction, and composition of velocities. Next we will discuss a relativistic mass. The rest mass of a particle is the mass of the particle as measured in the instantaneous rest frame of that particle. We designate or represent the rest mass by m naught. If A particle is moving with respect to an observer O with velocity v. Then observer O measures the mass of the particle as m is equal to m naught over 1 minus v square over c square under root, which is equal to gamma m naught. The relativistic mass is written as m is equal to gamma m naught, where m naught is the rest mass, ऐसा mass of particle जिसको हम रेस्ट फ्रेम में मेजर करते हैं उसे हम रेस्ट मास ऑफ पार्टिकल कहते हैं, जिसको हम डिनोट करते हैं m नॉट से. नाउ लेट्स कंसीडर द बाइनोमियल एक्सपेंशन which is valid for x mod less than 1, which we can write as 1 plus x to power n approximately equal to 1 plus nx. If we have n is equal to minus 1 over 2, then 1 minus x to power minus 1 over 2 approximately is equal to 1 plus 1 over 2x. If we put x is equal to v square over c square, then we can obtain m is equal to m naught over 1 minus v square over c square under root. Simplifying it, we get approximately equal to m naught into 1 plus 1 over 2 v square over c square, which can be written as m naught plus 1 over 2 m naught v square over c square. Let's multiply both sides with c square, then we obtain the expression mc square is equal to m naught c square plus half m naught v square. In this expression, we relate the relativistic energy to the rest mass energy plus the Newtonian kinetic energy of the particle. Relativistic energy is the mc square, rest mass energy is m naught c square, and kinetic energy of the particle is half m naught v square. This expression tells that if we add kinetic energy into rest mass energy, then we get the relativistic energy of the particle. Next, we will discuss relativistic momentum from Newton's second law, F is equal to ma. In particular, need conservation of momentum independent of reference frame. For this, using the Lorentz transformation to find the velocities does not conserve momentum. Therefore, we will need a new definition for the momentum, which can be written as the momentum can be written as mu over 1 minus u square over c square under root, which is equal to gamma mu. The relativistic force on a particle is written as F is equal to dp over d. By taking time derivative of momentum, we can obtain the force, which is the relativistic force on a particle. The relativistic energy, as with momentum, we need to redefine energy. For this, we will start with the work energy theorem or work kinetic energy theorem. हमें पता है कि वर्क को हम लिख सकते हैं as W is equal to इंटीग्रल एफ डी एक्स, और इसको हम फर्दर इस तरह लिख सकते हैं कि हम फोर्स की जगह पे उसकी वैल्यू पुट कर देते हैं, जो कि हमने अभी लिखी है dp/dt dx। अब अगर हम मोमेंटम p की वैल्यू यहाँ पे पुट कर दें तो फिर हमारे पास एक्सप्रेशन बन जाएगा इंटीग्रल d/dt mu/1 minus u square over c square under root dx. Now we will simplify this expression further. By integrating we get mc square over 1 minus u square over c square under root minus mc square, which can be written as gamma minus 1 into mc square. This term matches with the usual equation for the kinetic energy, half mv square for v very less than the speed of light. The second constant term is called the rest energy in last expression, which we can write as ER is equal to mc square. अब अगर यहाँ से हम टोटल एनर्जी का फार्मूला लिखना चाहें तो वो बन जाएगा रेस्ट एनर्जी प्लस द काइनेटिक एनर्जी, which can be written as E is equal to mc square over 1 minus u square over c square under root. S is a manifestation of energy, as we know that E is equal to mc square from Einstein's famous mass energy relation. We can rewrite the equation for the total energy in terms of the relativistic momentum. We can write gamma square is equal to 1 over 1 minus u square over c square. We can write it as c square over c square minus u square. Then we multiply gamma square with c square minus u square, and we get gamma square c square is equal to gamma square u square plus c square. From here we can write the expression for the energy. E square is equal to gamma square mc square to power whole square, which becomes gamma square c square m square c square, and we can further write it as m square c square into gamma square c square plus c square. From here we will introduce the momentum, and then this equation for the relativistic energy will be E square is equal to p square c square plus mc square whole square. This is the expression for the relativistic energy, which we can write in terms of relativistic momentum. This is very extremely useful formulation, which can also applies for massless particles, for example photons, where E is equal to pc, momentum into speed of light, which can be written as hc over lambda. As the speed approaches to the speed of light, relativistic effect starts arising, and therefore we will need to have relativistic forms of energy, momentum or force. These calculated formulas for relativistic momentum and energy, and also the rest mass, will be used in our next lectures.